Welcome back to ME 760 Engineering Analysis 1. So we will continue the same business of solving the higher order or nth order linear differential equations with constant coefficients. So let's start. So instead of writing, as we said last time, every time the equation, we will write an operator L operating over the function y, and this is as dny by dxn plus an minus 1 dy n minus 1 by dxn minus 1 plus an minus 2 dn minus 2 plus up to a naught y equal to g of x. And this is the inhomogeneous equation. So first of all, we'll start the solution as we stated last time, the solution of the homogeneous equation, meaning g of x equal to 0. So this is what we will start. So again, we will assume that the solution will be in the form that y of x equal to e to the power of lambda x, and of course you knew that the ith derivative of y will be just lambda to the power I e to the power of lambda x. So this is just the solution. Then if you substitute here, you will have an nth order polynomial in the variable lambda. So lambda n plus an minus 1 lambda n minus 1 plus an minus 2 lambda n minus 2 up to a naught lambda, a naught only without lambda, a naught is equal to 0, and we call this characteristic equation. Characteristic equation. Then we knew from the theory of polynomial that if AI's are real, then lambda i's will be either real or what? Complex conjugate pairs. Then we stated last time that we will look first at the case of distinct roots. What do we mean by distinct roots? Roots are what? Are different, and they do not duplicate or repeat. So the solution will be y of x will be c1 e to the power of lambda 1x plus c2 e to the power of lambda 2x plus c3 e to the power of lambda 3x up to cn e to the power of lambda n x. So from this equation we have how many roots here? N roots, and then you will have n what? N solution or n term. So this will be what? y1, y2, y3 up to y what? yn. And each one of those, if you substitute in the equation here, you should get what? When g of x equal to 0, if you substitute, you should get what? 0. You should get 0. If you substitute with any one of those, you should get what? 0. So this is why this is called, sometimes they call it the complementary function. Okay guys, complementary function. Because we solve the characteristic equation, get the roots, and then substitute here. So for complex conjugate, for complex conjugate pairs, what we will do for complex conjugate pairs, if we have lambda 1 equal to gamma 1 plus I omega 1, and lambda 2 is just the complex conjugate of this one, which is gamma 1 minus I omega 1. So those are two complex conjugate roots. So the solution will be what? If we have just second order, let's say second order linear differential equation, and the solution for the second order linear differential equation will be just, let's say, you will get something like a lambda square plus b lambda plus c equal to 0, and then you will get lambda equal to b square plus or minus square root of b plus or minus square root of b square minus 4 for AC over 2a. So if this will give you two complex conjugate roots, for example, so the first one is gamma 1 plus I omega 1, the second one is gamma 1 minus I omega 1 because of the plus and minus signs here. So if you got something like this, then you express your solution y as some constant c e to the power of the first root is what? Gamma 1 plus I omega 1 all multiplied by x plus c2 e to the power of what? Gamma 1 minus I omega 1 all multiplied by x. So we can call this c1 e to the power of gamma 1x, which is the real component of the complex number, multiplied by e to the power c1 e to the power of I omega 1x, and this is what? This is a complex number. So in order to solve this complex number using the Moivre, do you know the Moivre theorem? And this will give you what? E to the power of I theta r equal to r multiplied by cosine theta plus I sine theta. This is called the Moivre. How did you call it here? Huh? Euler, yeah, and also it has it's a French guy. Euler or the Moivre, sometimes they call them Moivre. Okay, Euler expansion. So you will give it so this is c1 e to the power of gamma, and what's e to the power of I omega 1? Cosine what? Omega 1 plus I sine omega 1 plus c2 e to the power of gamma 1 x multiplied by what? Cosine omega 1 minus I sine omega 1. Then you will have c1 plus c2 multiplied by e to the power of gamma 1x, this term and this term, and you will have what? Cosine omega 1 multiplied by cosine omega 1 plus I multiplied by c1 minus c2 e to the power of gamma 1 or gamma 2. Let me gamma 1 also. Gamma 1 multiplied by what? Sine omega 1 x. Okay, guys? And C1 and C1 and C2 are constants, so we can call this C1 prime. This is, we can call it C1 prime multiplied by e to the power of gamma 1x cosine omega 1 plus I C2 prime. We will call this C2 prime. C2 prime, and we'll call this C1 prime. So C2 prime multiplied by e to the power of gamma 1x sine omega 1x. So this is if you have, do you have any question?
Should it be cosine omega 1x also?
Thank you. Thank you. Okay, guys? Okay, guys? So if we have a combination of real and complex conjugate pairs, our solution for the nth order ordinary differential equation with constant coefficient will be the following. Will be y of x equal to the summation for Cj e to the power of lambda j x, and here j is the distinct real root plus summation over I, where I is the complex conjugate roots pairs, and this would be what? Ci e to the power of what? Gamma I x multiplied by what? Cosine omega I x plus Ci plus 1 e to the power of gamma I x multiplied by sine omega I x.
Do you need an I in front of your C? I plus 1. That's imaginary.
Okay, guys, do you have any question? So this is the case of what?
Having real and complex.
Having real roots, and those real roots are distinct roots, so you do not have any repeated roots in your solution, and maybe the distinct roots will be what? Will be real or will be complex conjugate pairs. So we saw the case for real roots, okay, and we check the case for complex conjugate roots, and we give a case of only two complex conjugate roots. Yes. So if you have a combination of this, you will have, let's say that you have n equal to 10th order differential equation. 6 of them are real, and 4 of them are complex conjugate pairs. So J will run from what to what here? 1 to 6. You have 6 roots, real, and here will run from 1 to 4. Yes. So 1 to 4. So one. So it will be 2 only, because they will be pairs. So it will be 2 pairs. Okay, guys. So it will be 1 to 2. So we will check now the case for multiple, if we have multiple roots. So we will suppose that L e to the power of lambda x is lambda n plus a n minus 1 lambda n plus 1 plus up to a naught. All of this will be multiplied by e to the power of lambda x. This is as before, exactly as before, but we can write this as lambda minus lambda 1 to the power of m multiplied by h of lambda multiplied by e to the power of lambda x, and we'll call this number 1. What do we mean here? We mean that the solution for this equation, this term is the same term like this. So the solution for this equation has m multiple roots. So this is m multiple roots. What's the multiple root here? Lambda equal to what? Lambda equal to lambda 1. So we have, let's say if this is 3, so we have lambda equal to lambda 1 3 times. So we have 3 times lambda 1. So this is multiple root. So when you solve the equation y square, I think minus 2 y plus 1, this will give you what? Y equal to what? Minus 1 minus 1, I think. Or plus 1 plus 1? Plus 1 plus 1. Plus 1 plus 1. Yes? Twice. Plus 1 and plus 1. Yes, guys? So y plus 1 plus 1. So this is just for second order algebraic equation. If you have, let's say, third order and all of them are 1, so in this case you will have what? 3 times lambda 1. So what's h of lambda? It's the remaining root. It's what? The remaining root. So lambda 1 is the multiplicity and m less than or equal to n. So if your equation is 10th order and this is 3 of the 10th roots are lambda 1, so 3 will be less than what? 10. So the maximum here is if you have 10 roots and all of them are what? Are the same, so m would be equal to what? Equal to n. Now, h of lambda will be the remaining distinct roots, and this will be just by from I equal to m plus 1 up to n of lambda minus lambda i's. So you knew what's this? You knew what's by?
Multiplication.
The multiplication. So this would be what? Lambda minus lambda m plus 1 multiplied by lambda minus lambda m plus 2 multiplied by lambda minus lambda m plus 3 until lambda minus lambda n. Okay, guys? And those are the distinct roots. So if you have 10, n equal to 10, and you have 3 of them are multiplicity or multiple roots, you have 7 non-multiple roots. So this will be what? Lambda minus lambda 4 multiplied by lambda minus lambda 5 multiplied by lambda minus lambda 6 multiplied by lambda minus lambda 7 until lambda minus lambda what? 10. Okay, guys? So if we differentiate the first equation, this equation here, if we differentiate it with respect to lambda, so differentiate differentiate 1 with respect 2 lambda. Why we are doing this? Can somebody tell me why we are doing this? We have 3 multiple roots out of 10. Why we are doing this? So we said last time that our solution, if we have distinct roots, those roots will be linearly what? Linearly independent. If you have 3 roots are exactly the same, do you still have linear independence? No. So we have to search for a linearly independent solutions for the 10th order differential equation. So those 3 roots, which are y1, 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 they cannot be a part of the linear independent solution. So we have to seek some other solution that will be a linear independence, okay? That will constitute a linear independence solution. So this is what we are looking for right now. We will differentiate this equation number 1 with respect to lambda and look for what's going on. So if you differentiate d by d lambda for Ly, this will give you m multiplied by lambda minus lambda 1 to the power of m minus what? M minus 1 multiplied by h as a function of lambda e to the power of lambda x. So you differentiate the first multiplied by the second, then you differentiate the second multiplied by what? By the first. So plus lambda minus lambda 1 to the power of m multiplied by the differentiation of the second, and the second is h of lambda e to the power of lambda x. What do you think when lambda equal to lambda 1? What do you think in this? When lambda equal to lambda 1, what do you think 2 will be? 2 will be what? Guys, 0. Why? Lambda 1 minus lambda 1 is what? 0. Multiplied by anything is 0. And lambda 1 minus lambda 1 is what? 0 multiplied by anything is 0. So 2 will be what? Equal what? 2 is equal to 0. So this means that what? That d by d lambda for our differential equation here, L of y equal to what? Equal to 0. Yes? So what does it mean? We can interchange the differentiation. You knew that L is just what?
It's an operator on y.
An operator on what? On y. This operator is just differentiation with respect to what? X. D by dx, dn by dx, dn minus 1 by dx, dn minus 2 by dx, and so on. Here we are differentiating with respect to what? With y. So this is d by dl of L, and what's L? Operated over, this is the solution, yes? The form of the solution y equal to what? E to the power of lambda x. So L is just a differentiation with respect to what? Dx, yes? dy by dx, dn by dxn, dn minus 1 by dxn minus 1, and so on. And then after we do all this for this equation, we will do what? Differentiate with what? With lambda, yes? So we can interchange. We can say that this is equal to L multiplied by what? D by d lambda e to the power of what? Lambda x. It is exactly the same. If you want to differentiate first with respect to what? With x, which is this operator L here is differentiating with respect to x. Or you can differentiate first with respect to what? Lambda, and then equate it to what? And then differentiate with respect to what? X. So this is what we are doing. After differentiation, d by d lambda of L e to the power of lambda x, this is equal to what? 0. If we interchange, this will be L d by d lambda e to the power of lambda what? Lambda x, and this is equal to what? 0 again. Yes, guys? So what's d by d lambda for e to the power of lambda x? X e to the power of what? Equal to what? Equal to 0. Yes? I just differentiate this with respect to what? Lambda, and it gives me what? X e to the power of lambda x. What does it mean this? This is the differential equation. Same differential equation. But instead of the solution is y, now I have the solution is equal to what? X e to the power of lambda x. So x e to the power of lambda x represent also what? A solution for the differential equation. Yes? So if e to the power of lambda x represent a solution for the differential equation, if I have a multiple roots, e to the power x e to the power of lambda x represent also what? A solution. So this means that x e to the power of lambda x is also a solution for the nth order ODE. Okay, guys? So, if we differentiate again this equation with respect to lambda again, so d2 by d lambda square of L e to the power of lambda x, this will give me what? Here is the first differentiation. M multiplied by lambda minus lambda 1, m minus 1 multiplied by this plus this term. Yes? Differentiate it again. So this will give you what? M multiplied by what? M minus 1 multiplied by what? Lambda minus lambda 1, m minus what? Minus 2. Yes? Multiplied by the differentiation with respect to lambda of what? H of lambda e to the power of lambda x. Yes? Yes? Plus h of lambda e to the power of lambda x. Oh, this is, sorry, I'm sorry. This term is not here. Multiplied by what? D by d lambda for this, multiplied by what? M lambda minus lambda 1 to the power of m minus 1 plus, what's the differentiation of the second term? M lambda minus lambda 1 to the power of m minus 1. Yes, guys? Multiplied by d by d lambda for h of lambda e to the power of lambda x plus, yes, plus lambda minus lambda what? 1 multiplied by the differentiation of the second, which is this. This will give you d2 by d what? Lambda square h of lambda e to the power of lambda x. Again, this will be at lambda equal to lambda 1. This will be equal to what? 0. So d2 by d lambda square of L e to the power of lambda x will be equal to what? 0. So this is to say that L d2 by d lambda square e to the power of lambda x is equal to what? 0. And what's this? x square e to the power of what? Yes? X squared to the power of lambda x. So x squared to the power of lambda x is also what? Is also what? Is also a solution. So if we do this m times, if we do this m times, we will notice that we will generate we will generate ym equal to what? xm minus 1 e to the power of lambda x. Okay, guys? And by the way, in all lambdas, we have to put what? Lambda 1. In all lambdas, we will put lambda 1. Because this is at e to the power of what? This is at lambda equal to lambda what?
1.
Lambda 1. So this will be xm minus 1 e to the power of lambda x. So that's for m identical roots, lambda I, for example, we will have m linearly independent solutions, and they are e to the power of what? Lambda I x. Let's assume that we have the 10th order differential equation, and we have lambda 1 3 times. Lambda 1 3 times. So what will be lambda I? Is lambda 1. Okay, guys? Lambda I is the repeated root 3 times. So the solution will be what? E to the power of lambda 1 x. And what's the second one? X e to the power of what? Lambda 1 x. And what's the third one? X squared e to the power of lambda what? 1 x. So those are three different solutions. Now we can build our what? Set of solutions. It will be what? Summation from I equal to what? M plus 1 to n of what? Ci e to the power of what? Lambda I x plus summation from I equal to 1 to m, and it will be what? X to the power of what? I minus 1 e to the power of what? Lambda I x multiplied by Ci. So those will be the linearly independent solution that you will get the distinct what? Distinct roots. Okay?
On that second term,
Yeah.
for e to the lambda ix, your lambda I would change for your...
It's only
So that
they will call it lambda because they are distinct roots. So we'll call it lambda if you have a distinct root. If this is only will be so if we have more than one distinct root, we'll call this is j, and this will be j from 1 to, let's say, L, where j equal to 1, this will be the first repeated root, j equal to 2, it will be the second repeated root, j equal to 3, it will be the third repeated root, and so on. So what's the solution? This is if the solution is multiple repeated roots, but the roots are what? are real. Yes, we have two situations when the roots are distinct. One is what? Real, and the other one is complex conjugate pairs. Yes? So what if your roots are multiple complex conjugate pairs? So you get what? Let's say you get 3 plus 5i and 3 minus 5i, but you get those 4 times. So the solution will be for multiple complex conjugate roots, it will be still the same. This is lambda minus lambda I minus I omega to the power of m, and lambda minus lambda I plus I omega I here to the power of m. By the way, I here is different from this. This is the complex number, the square root of -1, and this is just a running subscript. Okay, guys, so that nobody will have a confusion. I here is just the complex number, and I here is just a running subscript 1, 2, 3, 4, 5. Okay, guys, and the independent solutions will be just e to the power of lambda I x multiplied by cosine omega I x and e to the power of lambda I x sine omega I x, and you will have the second one will be x e to the power of lambda I x cosine omega I x plus I x sine omega I x e to the power of lambda I x, and up to e to the power of lambda I x to the power of m minus 1 cosine omega I x and x to the power of m minus 1 e to the power of lambda I x sine omega I x. So it is exactly the same as we did over there. So for the real solution, if we have m repeated roots, so if we have m repeated roots, we have what? If you have m repeated roots and this root is lambda I, how many solutions here you have? M. Yes, a 1 that does not have any x in it, then a 1 with x multiplied by it, then x squared up to x to the power of what? M minus 1. For the complex roots, we will have exactly the same. 1 that does not have any x multiplied in it. Okay, guys? Which is this one. This is the first complex conjugate pair. It does not have any x multiplied in it. Yes? So the second one will have what? X multiplied in it. The third one will have x what? X squared. And the fourth one? X cubed. And the mth one? Xm minus 1, xm minus 1. So it is exactly the same. Okay, guys? So now let's look for the particular solution. So we solve it now, the equation which is homogeneous. Yes, and we show how many cases now? 2 cases, a distinct root and a multiple root. And in each one we have how many cases? 2, real or complex conjugate pairs. So now let's look for the particular solution. And what do we mean by particular solution?
Solution to the inhomogeneous.
So g of x does not equal to what? Does not equal to 0. So this is what? Homogeneous, inhomogeneous what? Equation. So if the operator or the differential equation L, you will substitute in this differential equation with a function, with the function J is a function of the same class or type, same class or type as J, then look for a particular solution of the form P is general form of J class, and I will tell you in a second what do we mean by this. Okay guys, let's assume that our differential equation is equal to J of dny by dx to the power of n an minus 1 dn minus 1 y by dx n minus 1 a naught y equal to g of x. Okay guys, and this is equal to what? L of what? L of y. Okay guys, what if your g of x here is just e to the power of lambda x? So what you will do is try to choose a particular integral that's some constant multiplied by e to the power of lambda x. Okay guys, and then by substituting here for y equal to c e to the power of l or lambda x, once you substitute here, you will obtain what? You will, if you differentiate, it will be a function of lambdas and c's. The c that you do not know, you have to evaluate this c. Okay, guys. So if we look at this function, just by first guess, we can look for a guess for the particular integral, and this will be from the following. If you have your g of x, for example, is some constant multiplied by e to the power of gamma x, so this is g of x. This equation equal to k e to the power of gamma x. So we will look for solution c e to the power of gamma x for the particular integral. Okay, guys. If our function g of x is just kn x to the power of n plus kn minus 1 x to the power of n minus 1 plus blah 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 up to kn, we will again choose this to be cn x to the power of n cn minus 1 x to the power of n minus 1 plus c naught. So we will pretty much look at the g of x, which is the inhomogeneity part, and look for the form of g of x. If our form of g of x k e to the power of gamma x, we will look for a solution in the same form, in the same functional form, with different what? Coefficient. And this is called the method of determining the, it's called the unknown coefficients, a method of determining unknown coefficients. So because just you have to determine what? C in order to get the full solution for the particular integral. So what's your function if your function is k cosine omega x or k sine omega x? You will look for solution what? C1 cosine omega x plus C2 sine omega x. Okay guys? If your solution is k multiplied by e to the power of gamma cosine omega x or k e to the power of gamma x sine omega x, you will look for solution of what? E to the power of gamma x multiplied by again C1 cosine omega x plus C2 sine omega x, and so on. So if it is e to the power of gamma x multiplied by kn x to the power of n plus kn minus 1 x to the power of kn minus 1 up to k naught, so we'll look for a solution that's bn x to the n plus p naught all multiplied by e to the power of gamma x. For the cosine and sine or sinh omega x, you will look again for C1 cos omega x plus C2 sinh omega x. So the rule is if you will have a summation of those functions, let's assume that you have a summation of k e to the power of gamma x plus k2 cosine omega x, so you will do exactly the same. You will do what? You will have also a summation c e to the power of gamma x plus c1 cosine omega x plus c2 cosine sine omega x. Okay guys? So I think it's time now for taking off, but before finishing, I think I brought it here. There is a handout that's in the handout section by Professor Ken Schultz, and this is called the particular solution for linear ordinary differential equations, and it shows you the form of the function and what will be your choice, what to choose in order to solve this one. And this is again is called method of determined coefficients. We have to determine what are the coefficients. So you knew what's the functional form, but we do not know what are the coefficients, and we need to determine those coefficients. This is called the method of undetermined coefficient. So the solution for the particular integral, it's a little bit tricky. It's not systematic as the solution for the homogeneous equation. So I will stop here and continue next time.